Let's go ahead and do a few more examples of integration. And I want to work with both definite integrals and indefinite integrals because when we are doing integration, we might have a reason to look at a definite integral or it might just be an indefinite integral. So we need to be able to move interchangeably between the two, applying our rules as we go. So let's just quickly review what a definite integral is versus what an indefinite integral is. So a definite integral, we will have our bounds, our integral, our lower and upper bound from a to b of f of x dx, and this will give back a number. So we will get back a number when we're taking a definite integral. Because in order to actually find the definite integral, we're going to use, this by the way is the fundamental, it's just a restatement of the fundamental theorem of calculus. Says that this integral from a to b of f of x dx is equal to capital F of x evaluated from a to b, which is f of b minus f of a, and this is all where capital F prime of x is equal to little f of x. In other words, capital F of x is the antiderivative of little f of x. Now, just on another note, what this represents, what this number represents the net area between y equals f of x and the x-axis. So, it does also have this graphical meaning to us. It's representing the net area between y equals f of x and the x-axis. Okay, so that was the fundamental theorem of calculus and our summary of a definite integral. Now, an indefinite integral gives us back the antiderivative. So if we have no bounds on it, we're just asking to find the integral, the indefinite integral of f of x dx. That will be capital F of x, where, again, capital F prime of x equals, capital F prime of x equals little f of x, which just means capital F of x, in both of these cases, I didn't write it up above, but it just means that capital F of x is the antiderivative of little f of x. That's what this means. Now, when we get this function, we will also have an integration constant, a constant from finding the antiderivative. So this actually represents a function. We get back a function, not a number like the definite integral. We actually get back a function. Or more specifically, we get a family of functions, and that's because of the plus c. We will have that plus c, which gives us an entire family of functions. Okay, so that said, that's just a quick review of where we're coming into this video with a definite integral, indefinite integrals. We've worked with both, and now we're just going to do examples with both. We're going to go ahead and use the indefinite integrals that we're familiar with that come right out of our knowledge of antiderivatives. So we've got this table, and this is what we're going to work with. And now let's just do some examples. Okay, so for all of these examples, we're just going to be evaluating the integral. So if we have the integral of the secant of x times the secant of x plus the tangent of x, that is not a product that immediately sparks in my mind familiarity with antiderivatives, right? I don't have an antiderivative that is exactly equal to the secant of x times the secant of x plus the tangent of x as a quantity. But with a quick little distribution, I'm going to see two functions who I do actually know their antiderivatives of. So I'm going to go ahead and distribute. And, sometimes when we're working with integrals, we have to do a little simplification, just like when we're working with derivatives. Sometimes we have to do a little simplification before we can take a derivative. Sometimes we got to do a little simplification before we can actually integrate, find an antiderivative. But now I'm looking at it and I can pretty clearly recognize the antiderivative of secant squared will be tangent, and the antiderivative of the secant of x times the tangent of x will be secant. So this is, and it's just an indefinite integral. So we're looking for the general antiderivative. So we're going to get tangent of x plus secant of x plus c. Because I do have an integration constant, can always check, take the derivative, right? Go backwards, take the derivative. Derivative of tangent is secant squared. Derivative of secant is secant tangent. Derivative of a constant is 0. So don't forget, when we do have indefinite integrals, we're finding a family of functions. That plus c gives us the family because they all have that general shape, tangent of x plus secant of x, but they could be shifted vertically up or down and still have the same derivative. Okay, let's look at another one. Let's take a look at this one. So again, indefinite integral, so we're just going to be finding the general antiderivative here. I notice here, and we've worked with these a few times now through these videos, that I have a f of k times x. So remember when I integrate f of k times x, just as a quick reminder, that this is going to give me, and it's basically, in my mind I think, okay, I'm undoing that chain rule. So I'm going to have 1 over k times the antiderivative of little f of x, capital F of x, evaluated at kx plus c. So I see that 5x right there, so I know I can find the integral of the cosine of x. The integral of the cosine of x, in fact, is the sine of 5x. But because I'm finding the antiderivative I'm integrating, I'm going to have a 1/5. And then this guy, this minus 1 over the square root of 1 minus x squared, well, that's just the inverse sine of x. And I do have my plus c. And that, in fact, finding indefinite integrals is easier. We don't even have to, once we found the integral, we don't even have to evaluate it. So it can often be easier to find indefinite integrals. We're done. Once we've got our antiderivative, once we've integrated, there's not that second step that definite integrals has, which is to evaluate across the bounds. Okay, so once again, though, those will pop up periodically where we'll have that, just that slight variation on x, right? We have just a constant times x, and we adjust for that with the 1 over k. And that, again, is just backwards of chain rule, because when we're taking a derivative, if we have k times x composed into a function, we multiply by k. So finding an antiderivative, we're going to divide by k or multiply by 1 over k. Okay, so let's keep going. This time we're integrating. This time we have a definite integral, and we're integrating from 1 to 4. This function, it's a function of t, but we're integrating with respect to t. So notice the dt, the differential is with respect to t. So first thing we're going to do here is notice that there's probably a little rewriting that I want to do here, because I've got that quotient, and I can't integrate that quotient, but I can apply power rule if I were to simplify and divide everything by t squared. So I'm going to end up with t to the negative 3/2, because this right here is t to the 1/2, and I'm dividing by t squared, so subtracting 2, subtracting 4 over 2, so I get negative 3/2. Then I'm going to have minus t to the negative 1 dt. Now, another way to think of t to the negative 1, of course, is to think of it as 1 over t. Okay? So either way, you can think of it as t to the negative 1, or you can think of it as 1 over t. But again, this piece is the one piece that the 1 power, 1 exponent on x, or in this case t, that we can't actually just apply the power rule to. So we have to recognize that 1 over t, t to the negative 1, actually has an antiderivative of the natural log of t, natural log of the absolute value of t. So when I go to actually find this antiderivative now, I can apply the power rule to the first part. So t to the negative 3/2 becomes t to the negative 1/2. And now I would be dividing by negative 1/2, but dividing by negative 1/2 is the same as multiplying by negative 2. So on the next line, I'm just going to go ahead and write that. And then minus 1 over t is minus the natural log of the absolute value of t. Now, I don't actually need the absolute value of t, because t is running from 1 to 4, or we're evaluating t from 1 to 4. So the bounds have already restricted t to positive values, so I don't really need the absolute value anymore. I can leave it in there. It's not harmful. It's just extra notation that's not necessary. So I'm going to write it, and then I'm just going to go ahead and switch those to parentheses. And that's because of the bounds. Okay? So again, let's make a little note. So I can drop that because the bounds are positive. And we were already on a positive interval from 1 to 4. Okay, now I have, just as a note here, I already have the antiderivative, right? I have negative 2 t to the negative 1/2 minus the natural log of t. If this had not been a definite integral, if it had been an indefinite integral, I would slap a plus c on this thing and I would be done, okay? So, but I'm not, right? It's a definite integral, so now I have to evaluate it. So now I have to actually do, right? I need to calculate f of 4 minus f of 1 since it's a definite integral. And so let's do that. So we're going to plug in. Oh, just one little note on this t to the negative 1/2. I'm going to go ahead and just rewrite that on this line. Write that as negative 2 over t to the 1/2. No, you know, t to the 1/2. I guess another way to write that would be to write the square root of t. And I think I will, since I'm going to be actually plugging in 4 and 1. So then this is going to end up being negative 2 over the square root of 4 minus the natural log of 4 minus negative 2 over the square root of 1 minus the natural log of 1. Now the natural log of 1, by the way, is 0. So that is 0. And let's see, we get negative 1 minus the natural log of 4 plus 2. So we get 1 minus the natural log of 4. And I could approximate that. I guess I could pull out my calculator if we wanted to, but I'm going to go ahead and leave it exact. So we'll go ahead and leave that exact for now. Okay, let's maybe do one more example. And then let's wrap this video up. We'll wrap this video up with what is called the net change theorem. So bring this all back to applications again here at the end. So let's do one more example though, and this one just has a, just kind of a fun little combination of 4s, x's, and exponentials, right? And I just kind of, created a function that had exponentials and power functions and constants kind of all mixed in, so we can be clear about what is what. And it is, by the way, a definite integral from 0 to 1, so in the end we're going to have to evaluate it. So keeping in mind as I go through this that we need to be clear about what we're working with. We've got 4x to the first, that is a power function. X to the fourth, power function. 4 to the x, exponential. E to the x, exponential. E to the fourth, constant. Okay, so as we go through these, I'm going to say that, but it might happen kind of quickly. So as we go to integrate, we're going to get 4x squared over 2 minus x to the fourth, x to the fifth actually, minus x to the fifth over 5 plus 4 to the x over the natural log of 4. So remember, when we have anything other than base e, if it's a to the x, that the antiderivative, or the integral now, is going to be a to the x over ln of a. Minus e to the x is just going to be e to the x. And e to the fourth is a constant. And so when we integrate a constant, we get e to the fourth times x. And now we're evaluating this from 0 to 1. So let's see, is there not much to simplify? I think I'm just going to simplify this part here without rewriting and just write that as 2. Okay. And now let's go ahead and just throw those two bounds in and subtract. So we're going to get 2 minus 1/5 plus 4 over ln of 4 minus e to the first plus e to the fourth minus, and then we're going to get 0, 0, plus 4 to the 0. 4 to the 0 is actually just 1, so I'm going to write that as 1 over the natural log of 4 minus 1 plus 0. And let's see here. So we end up with, let's see, 2, we get 3 minus 1/5. So that's actually 15 fifths. So we're going to have our constant is going to be 14 fifths. Plus we've got 4 natural log over natural log of 4 minus 1 over the natural log of 4. So that's going to give me a 3 over the natural log of 4 and minus e plus e to the fourth. And there is my answer there with just a little bit of simplification. It did not carry down those, so I will now. Minus e to the first plus e to the fourth. And there's our answer for our definite integral, and we will just leave it exact. So I want to end this video with one last theorem, and actually end the lecture on this section with this last theorem called the Net Change Theorem. And the integral of a rate of change, just notice that this is not the fate of change. Sorry, that was a funny typo there. The integral of a rate of change is the net change. So if we're actually taking a definite integral from a to b of f prime of x, which is a rate of change, remember that a derivative f prime of x, anytime we take a derivative is a rate of change of the original function. It's the rate of change of f of x. Okay? So f of x, if we have a function f of x and we're talking about its rate of change, how that function is actually changing. We'll look at some examples here in just a second. Let me just squeeze that in there. F prime of x is representing the rate of change. So f prime of x is a rate of change. So if we integrate a rate of change, just by the actual fundamental theorem, we get back the original function f of x evaluated from a to b, and we get this net change, this f of b minus f of a. So this, this is a theorem, and we're now talking about context, but it really is just the fundamental theorem of calculus in this context of rates of change, which is what a derivative is, and we've worked with them for weeks, months now. So let's just look at a couple examples. I pulled some of these examples off to the side so that we would have a little more space. So let's do them over here. So let's just suppose we have w prime of t, and it's representing the growth of a child in pounds per year. Well, if what we want to find is the integral, we want to talk about what does that integral then represent, the integral from 5 to 10 of w prime of t dt. Well, what would that represent? Well, let's look at it. So w prime of t, to start off with, is a growth, represents the growth of a child. That's a rate of change. So it represents the growth, and growth is a change, rate of change, in child's weight. Then w of t, the antiderivative, would just be the actual child's weight. Okay, at t years per year. T is in years. I guess we'll write that too. T is in years. So just the context of the problem, given the derivative representing this rate of change, this growth, when we talk about growth, decay, right? Those are things that are rates of change. So we're talking about the growth, the derivative is a rate of change, and the integral then from 5 to 10 of w prime of t dt by the fundamental theorem is going to just be w of t evaluated from 5 to 10. We don't even need a function. We can just write it generically, and it's going to be w of evaluated at 10 minus w evaluated at 5. So what does that represent? Well, that represents the weight of the child at age 10 minus the weight of the child at age 5. It's the net change. It's the change in the weight. Now, of course, you don't have to write all this down. I just want to be really clear about we have context here. And so what does this mean? Well, it just simply means that the integral from 5 to 10 of w prime of t dt represents the net change in the child's weight from ages 5 to, or years 5 to 10. I guess we didn't say age, we said per year. So w prime of t dt integrated from 5 to 10 represents the net change in child's weight from age or year 5 to 10. And it's really, once again, just taking what we already have, the fundamental theorem, and putting it in the context of a rate of change with some specific context, right? In this case, a rate of change being a child's growth in pounds. Okay, so what if we had this one? Water flows from the bottom of a storage tank at a rate. So again, we're given a rate. This is the rate. In gallons per minute, where our time is going to run from 0 to 250 minutes. Find the amount of water that flows from the tank in the first 30 minutes. So if we want the amount of water that flows from the tank in the first 30 minutes, that's going to be represented by 0 to 30 of the rate of change, R of t. That's going to give me the net change in the water tank, storage tank. So what would that be? Well, that's simply the integral from 0 to 30 of 2000 minus 8t dt. Notice, by the way, my differential is matching my function being in time, dt. Oh, and I just had to take a minute to double check. 30 minutes, and we are in minutes. This was in per minute. Of course, you have to match your units, and they do match here, but quick check on that one. And so what's this going to be? Well, this is just a definite integral, so 2000t minus 4t squared, because we have negative 8 divided by 2, t squared, evaluated from 0 to 30. So this is going to be 2. Now we just plug in our bounds, evaluate it, across the first 30 minutes. And we get 56,400 gallons have flowed from the tank over the first 30 minutes. Okay, so just taking what we've done and applying it in context now. So taking the fundamental theorem and saying now, if we're actually thinking of and we have some context for that derivative as a rate of change, the integral then of the derivative from a to b is going to represent the net change of the original function.